In this video, we're going to be talking about how we actually set up a redox reaction so that electrical energy is being involved here. And we do that through what's known as an electrochemical cell. So this is a device containing a redox reaction. That can interconvert electrical energy and chemical potential energy. So there are two different kinds of electrochemical cells. The first is known as a galvanic cell. Sometimes you'll also hear these referred to as voltaic cells, but galvanic is the one we're going with. So these take chemical potential energy and they convert it into electrical energy. So in a galvanic cell, we have a thermodynamically favored reaction. So for a galvanic cell, our cell potential is always positive. So a thermodynamically favored reaction occurs, generating electricity. So galvanic cells are batteries, essentially. They produce electrical current, they produce electrical energy from a chemical reaction. So anything you have in your life that contains a battery or that runs on battery power, that battery is a galvanic cell. We're going to talk about the kind of typical lab setup of a galvanic cell, which looks different than what is, say, inside your phone, but it has all the same parts and pieces. It is functionally the same thing as any battery operated or any battery that's operating a device. We're creating electricity from a chemical reaction. So every time you use your phone, you're doing chemistry, whether you realize it or not. You cannot escape the chemistry. The other type of electrochemical cell is known as an electrolytic cell. Which takes electrical energy and converts it into chemical potential energy. So going the opposite direction in terms of the type of energy transition we're doing here. So in an electrolytic cell, what we have is a thermodynamically disfavored reaction. So that means our cell potential is less. Oops, a thermodynamically disfavored reaction. Sorry, missed a word. Thermodynamically disfavored reaction is forced to occur. So since it is disfavored, it doesn't occur spontaneously on its own, but we make it happen anyways by applying an external source of electrical energy. So this is akin to recharging a battery. So any type of rechargeable battery is capable of functioning as both a galvanic cell and an electrolytic cell depending upon the circumstances. So when you're, say, using your phone or using your laptop throughout the school day and the battery is draining, it is functioning as a galvanic cell. It is producing the electrical power necessary in order to power your device. When you plug it in at night to recharge it, now that battery is functioning as an electrolytic cell, that you are putting in an external source of electrical energy coming from the wall outlet that you plugged into, in order to force that reaction to run in the disfavored direction so that you will have stuff available to produce power the next day. Essentially, throughout the day, you're converting reactants into products, using up reactants and producing products. And then when you recharge your battery, you're running it in the opposite direction to make those reactants again so that they're available to power your device the next day. So for the rest of this video, we're going to be focusing on galvanic cells. We'll come back to electrolytic cells later. So in a galvanic cell, in order to harness the power of redox, in order to actually generate an electric current from a redox reaction, we need to set it up in a particular way. So what needs to be true is that it must be set up with the half reactions occurring in separate containers. That are connected by a wire or some kind of circuitry. In the diagrams that we draw, it'll just be a pretty simple wire. There might be like a voltmeter or a light bulb or something along it. In an actual device, this wire is the circuitry of the device itself. So in between the cathode and the anode is all the wires and stuff that run through your phone to make it work. So we have our half reactions set up in two different containers that are connected by a wire. These containers have names. The anode is where oxidation occurs. It's the oxidation site. There we go. And the cathode is where reduction occurs. And essentially what we're doing here is we're generating an electric current by making those electrons travel through the wire. So the way this is set up, oxidation occurs at the anode, electrons are lost in oxidation, electrons are lost at the anode. They have nowhere to go but to travel through this wire. And that is what generates our electric current. Electricity, at its simplest description, is just a movement of charge in one net direction. So if you have a bunch of charged particles all moving in the same direction, that is fundamentally electricity. That is fundamentally an electric current. So we're forcing all of these electrons to move in through this wire from the anode to the cathode, all in the same direction. That is generating our electric current. So once we get everything set up and connected, your reaction is thermodynamically favored. It just goes, it just starts. So once everything is connected, your reaction is going to proceed in the spontaneous direction. So the cathode always contains reduction, we know that, but it specifically always contains the reduction half reaction with the highest standard reduction potential. So you always have two half reactions to make a whole reaction, to make a whole redox reaction. Whichever has the higher standard reduction potential is going to occur as a reduction. The anode will always contain the oxidation half reaction with the highest oxidation potential. Which corresponds to the lower reduction potential. We learned in the last video that the oxidation potential and the reduction potential are just equal and opposite. So the lowest reduction potential, when you flip the sign, is going to become the highest oxidation potential. So this combination of things here forces Enot cell to come out zero. Greater than zero, sorry. So when this is true is when your cell potential comes out positive, and the cell potential for a galvanic cell is always positive because it is always a spontaneous reaction that is occurring in the cell. So understanding this can allow us to figure out what's going to happen if we combine certain combinations of materials. So let's say a student wants to construct a galvanic cell. And they have the following materials available. For one half cell, they want to use a solution containing aluminum 3+ ions and some solid aluminum. And for the other half cell, they want to use a solution containing some copper 2 ions and some solid copper. So what we need to do here is figure out, or one thing we can do here, I guess, is determine the reactions that are going to happen at the cathode and at the anode. So we're going to need a table of standard reduction potentials. Okay, there it is. Sure. So make this a little bigger. Our cathode reaction is always going to be whatever is the highest standard reduction potential that could occur with the stuff that we have. So in one container, we have aluminum 3 and aluminum solid. In a different container, we have copper 2 and copper solid. So what we want to do is look to this list to identify what are the standard reduction potentials for the reactions involving those things. So why don't you pause here and take a moment and try and find the standard reduction potentials associated with both of these combinations. So looking at what we've got here, we have aluminum 3 and aluminum solid. We find that combination down the bottom here. with a standard reduction potential of negative 1.66. And we have copper 2 and copper solid right here with a standard reduction potential of 0.34. So we had negative 1.66 and positive 0.34. So whichever of our standard reduction potentials is higher is the thing that is going to happen at the cathode exactly the way it is written on this sheet. So that is the copper combination here. So this is our higher Enot red. So that is going to occur as a reduction at the cathode. So our cathode reaction, we can literally just copy off of this list. So our cathode reaction will be copper 2 plus 2 electrons forms copper solid. For the anode reaction, our aluminum up here was our lower standard reduction potential, which means it's going to occur as oxidation at the anode. So that means that we're going to take the reverse of this reaction. Since it's written as a reduction, we're going to take the reverse reaction, and that is what will happen at the anode. Since reduction and oxidation are just opposite processes, flipping the reaction gets us the oxidation. We can also calculate the value of Enot cell, which we learned how to do in a previous video. So why don't you pause here again and do that now. So we know that Enot cell is just equal to the standard reduction potential plus the standard oxidation potential. So our standard reduction potential is going to be exactly as we found it on the list for our cathode reaction. For our anode reaction, it's going to get flipped. It's going to get reversed. So since we did the reaction in reverse, we changed the sign on the potential as well to get our oxidation potential. Since this one's reduction, the reaction is actually happening as an oxidation, so we're changing the sign. So our cell potential is going to be 0.34 volts plus 1.66 volts for a grand total of 2.00 volts. And we can also think about the overall reaction that's happening in the cell. So these two half reactions are occurring in separate spaces, but they are still interacting through this wire through the transfer of electrons. So we can write the net reaction that's occurring in the cell. Just like we have in the past, by combining our two half reactions, but making sure that our numbers of electrons gained and lost are equalized first. So pause here one more time and do that on your own. So what we need to accomplish here is equalizing our numbers of electrons lost in oxidation and gained in reduction. We currently have 2 being gained in the reduction, 3 being given off in the oxidation. So we're going to need to multiply all of our coefficients in the cathode reaction by 3 to get us to 6 electrons, and all of our anode coefficients by 2 to get us 6 electrons there as well. So now these numbers match. Our electrons will cancel out, and we can just add our two reactions together. So the net reaction occurring in our cell will be 3 copper ions plus 2 aluminum forms 3 copper and 2 aluminum ions. So I want to talk a little bit about what the setup for these cells actually looks like. So again, we're going to be looking at a very lab-oriented setup. An actual battery has the same parts and pieces, just the physical shape of it is very different. So I have a kind of general diagram here of the setup, and we're going to be using the same example that we were just working with above, where we have one of our half cells containing aluminum 3 and aluminum solid, and one of our half cells containing copper 2 and copper solid. So let's put the aluminum on the left. Convention is typically to put the anode on the left in these types of diagrams. It is not always followed at all. That is most common. So essentially what we have here is 2 beakers. So we have 2 different beakers. One of them contains a chunk of solid aluminum. So this rectangle here would be like a strip of aluminum metal. Ignore the colors. And that strip of metal is partially submerged in an aqueous solution containing the aluminum ions. So in that solution, we would also need there to be some kind of anion just to balance the charge, only because we can't have a bucket full of cations. So we would perhaps have something like nitrate ions in here as well. They're not really doing anything chemistry-wise, just spectators. But for the sake of physics, we need to have a neutrally charged beaker full of stuff, so we need some anions in there. So we said that the aluminum reaction was what was happening at our anode. So this chunk of metal is our anode. Sometimes you will also hear the entire beaker referred to as the anode, but the specific electrode, the actual place within that beaker where oxidation is going to happen, is the surface of that chunk of metal. So oxidation happens here. On the other side, in our other beaker, we have a strip of copper metal partially submerged in a solution containing copper ions. So those were our 2 different half cell materials. We had aluminum solid and aluminum 3, copper solid and copper 2. The copper was our cathode reaction. So this piece of copper is our cathode, which is where reduction happens. So we have these 2 separate containers. You'll notice that we do have a few other things in this diagram as well. We mentioned our wire, sometimes also referred to as the external circuit. Same thing. This is intended to just be like a voltmeter or something, not a super important part of the diagram, but that would measure the voltage that's being produced by the reaction. If you were using this to power some kind of device, this is where it would go. If you were trying to light up a light bulb, it would go right here. If you were trying to power your phone would be plugged in here. If the rest of this were a real battery, this would be the circuitry inside that device. And so this is where electrons are traveling, is through this wire. So we have electrons traveling from the anode to the cathode through this wire or through this external circuitry to power whatever it is we are trying to power. And they always travel anode to cathode. Since oxidation is happening at the anode, that is where electrons are being lost. So the electrons lost at the anode as part of the oxidation travel through the wire to the cathode, where they are used for reduction. So our anode is losing electrons. They travel through this wire, and when they get here, they're used to reduce something. So the other piece that we have here that I haven't talked about at all yet is what is known as the salt bridge. So the piece of equipment being depicted here is a glass tube, is a U-shaped glass tube that is filled with some kind of aqueous solution. Some kind of solution containing ions. And what the salt bridge does for us, the salt bridge is absolutely necessary in order to create a functioning cell, because this allows for ion flow between containers, which is the only way that we can maintain balance of charge. If we think about what's happening in this cell for what we've described thus far, is we have electrons moving from our anode to our cathode. If that was the only pathway between these two containers, we've got a bunch of negative charges all going in the same direction, and we would very quickly have a bucket full of negative charges and a bucket full of positive charges left behind, and that cannot happen. It just doesn't. So we have to have a way for the charges to equalize themselves. Within a given container here, you have to have a net zero charge. So this is what's essentially completing our circuit. That we need a complete circular pathway for charges to be able to flow in order for this to actually work. Without a salt bridge, if you put everything else together, absolutely nothing happens. So within our salt bridge, we have electrons traveling this way. We have negative charge flowing left to right, which means that negative charge also wants to flow right to left, and positive charge also wants to flow left to right as well. So what we find inside the salt bridge is that cations are going to want to go this way, and anions are going to want to go this way. So we have both positive and negative ions in there, just traveling in opposite directions. So we get this net flow of ions through the salt bridge that helps to balance out the charges being transferred via the electrons in the wire. So one other thing to think about here is what's actually happening at the molecular level. So just a little refresher here for what our anode and cathode reactions were. Anode reaction was solid aluminum reacting to form aqueous ions and electrons. Our cathode reaction was copper 2+ aqueous, grabbing 2 electrons to produce copper solid. So in the anode, our solid electrode here is reacting and turning into aqueous stuff. It's dissolving gradually. So our solid over here is being consumed in this reaction. So this is one reason or one possibility for why some batteries are not rechargeable, is that if this completely dissolves, there's nothing to really reverse. You can't like rebuild onto it. So not all reactions are going to be reversible, hence not all batteries are rechargeable. But like your typical AA, AAA type batteries can't be recharged. There are rechargeable versions of them, but your just basic alkaline zinc batteries are not reversible. So in this case, our solid electrode is dissolving into the solution. The mass of this aluminum is actually decreasing as this battery operates. On the other side, copper ions are producing additional solids. So they're actually plating on to that copper electrode in this reaction, making more and more copper. So electrochemical reactions or redox reactions are one of the ways that pure metals are obtained. Many are mined from the earth, but some are not available in nature in great quantities, so we have to do a redox reaction in order to produce them, or to produce them in great quantity. So this is generally what a galvanic cell looks like in the lab. Batteries have all the same parts and pieces, just set up a little bit differently, typically more in layers as opposed to like buckets like we're looking at here. That your salt bridge will be like some kind of porous membrane between two portions of the battery. And then your cathode and anode are kind of at either end, and that's what, when you put your battery in, the two ends connecting is what completes everything. But otherwise, they're fundamentally the same.